Hi everyone, so I'm Nicolas Heurtel. I'm a PhD student in Quandela with the theory team with Shane and also with the Université Paris-Saclay. And today I will present you the LOv-Calculus, so a graphical language for linear optics. So it was a work done by 5 people, so 2 from Quandela, me and Shane, and 3, so Alexandre Clément, Simon Perdry, and Benoit Valiron. So first, I would like to introduce to you what is a graphical language. So of course, we'll talk about LOv, but before presenting LOv, I would like to talk about another language, a language I'm trying to be better every day, which is English. So basically English, in English we have some words, some definitions for each word, and also with the words we can make sentences. For LOv, basically the generators are linear optical components, but instead of words and letters, we have figures, graphics. Each figure has an equivalent of a definition, so basically we call that the semantics. So each component has a process represented by a matrix. And finally, when we add the components together, we have what we call circuits. So here, linear optical circuits. Okay, but so we have a language, but well, it's not very useful at that point. So what can we do? The first thing we would like to do is to compare the elements of our language. For example, if I have 2 linear optical circuits, I would like to know if both of them are the same process. If we keep the equivalence with the English language, imagine that you have 2 sentences, and we just like to know if the 2 sentences are the same, basically the same semantics. The thing that you can do to know that is to use the dictionary for English or the matrices for the circuits, so basically to use the semantics. However, it's quite heavy, it's like a little boring, and I like to do the math, so we like to compare both elements, but without using the semantics, directly with the graphics. In order to do that, we introduce an equational theory, basically a set of equations on the circuits, so not on the matrices. So here are the equations. And which is cool with this set of equations is that it is complete. With the equations, we can rewrite any circuit into another if they are equivalent. So we can compare any elements with the equations. However, as you can see, there are a lot of equations, so we try to be a bit simpler this time, and we just introduce like a smaller set of equations, which are basically linear optical circuits, but only with phase shifters and beam splitters, as you can see. And so for that smaller subset of equations, we have also shown that it is complete. So given any circuits with the components of beam splitters and phase shifters, we can rewrite one into the other. Here we have the equations, and I would like just to introduce some example of what can be used for the equation. First example I would like to introduce is about universal shape that the circuit can have. So basically, you can represent the process, the linear optical process, with a unitary, and it has been shown that in 1994 that this unitary can be decomposed in a triangular shaped circuit. So like that. So like any unitary, for any unitary, you can have a linear optical circuit with a triangular form that represents the process. Later, a bit later, there was another result that showed that we can also have a rectangular shape for the same unitary. And so it is like far better shape because it's more symmetric. The depth is shorter. And so basically you have less noise for the same number of components. And so what is cool is the LOv-Calculus is like you don't have to think about the matrix anymore. Here we have 2 algorithms, so one from the 90s and the other like more recently. However, with the LOv-Calculus, you can just rewrite one into the other, basically just with the rewriting rules. So it's very cool because we can also find new schemes, other shapes that, for example, the triangular or the rectangular. And then we can aim to other universal forms and also like to have a better insight about that. So I would like to introduce a bit more about the process to go from the triangular to the rectangular shape with an example. So remember the rewriting rules at the beginning? So there is one which is specific, which changes the shape of the circuit. So here you can see we have a triangular with a 1 beam splitters on the top, and here the 1 beam splitters in on the bottom. And with that rule, we can change the shape of the circuit. So imagine that you have a triangular that we know how to do. And imagine the red beam splitters, we like to transfer the red beam splitters on the left. So it will become a blue one here, for example. So we have reshape one part of the circuit. And we will continue again with the red one, continue again, so that all the red will go to the left in blue here. And little by little, we can see that we have basically reshaped our circuits from a triangular shape to a rectangular shape. So it is basically what I've shown earlier to escape from the patent. And on the final examples, so there are many, but I just pinpoint some of them. This paper is basically, imagine you have still a rectangular shape, but instead of having phases a bit everywhere, here you have layers of phases. And it has been shown that if you have some noise, for example, here you have a +5 phases here, you can propagate the phase on the left here with a minus phase on the right. And if you want to remove that phase again, you propagate the phase on the right, and you have here a phase on the left. Everything in that paper can be reproduced by the LOv-Calculus because we have shown the completeness. Another example, so it's not basically rewriting circuits with phases, beam splitters, etc. But it's like an equivalent way of thinking. In that example, it is not a phase here, but a noise, like lost particles. And so it had been shown that if you have symmetric noise, it can also be propagated like we can propagate phases. So it's a very very interesting example because it can be shown that we can reuse the rewriting rules, not to rewrite circuits, but to model some noises in some circuits and to use again the same process. So let's go for the conclusion. Here we have presented the graphical language with both spatial improvisation and coding. So basically we can write any circuit with polarization and spatial encoding with beam splitters and phase shifters. We have also introduced an equational theory, and so we have shown that the set of equation is complete. So basically we can reproduce any result in quadratic rewriting. We can rewrite any circuit which is equivalent into another. And also we have shown a rewriting system and in the rewriting system to converge to what we call normal forms. And finally, the perspective. So as you may have understood with the graphical language and at least the LOv-Calculus, is that we don't talk about photons. So the semantics contain only sources and detectors with 0 photons. And so we like now to go further and to not only think of linear optical circuits, but also linear optical circuits with photons and with conditions of detecting some photons on some wires. And finally, as you may have seen, the beam splitters have a parameter for the reflexivity. And in practice, that beam splitters, we do that with the Max-Zehnder interferometer. So we only with 50-50 beam splitters. And for now, the generators don't have the 50-50 beam splitters. So maybe we like to change a bit the rules. So the 50-50 beam splitters are in the generators. At the end of the presentation, thank you very much for your time. If you have any question, please ask me, ask someone in the team. Follow also the developing and the future of LOv because we'll be sure to improve that. Thank you very much.